Okay, here we are. We're looking at practice 16D. And here's how we're going to do this. This first one, it's kind of a curveball, but not really. What's it saying? It says that when you react 1 mole of methane, you get 890 kilojoules of energy burned off. Okay, well, we don't have a mole. We got 3.2 grams. Well, let's find out how many moles we have, because if 1 mole is equal to 890 kilojoules, and we don't have a mole's worth, well, let's find out. So here's what I'm going to do. I'm simply going to say this. How many kilojoules of methane, CH4, would be the equivalent of 3.2 grams of CH4 if we know that the molar mass of methane is 16 grams. 1 carbon is 12. 4 oxygens, they're each 4, that's 16. And that's 1 mole. Why do I keep writing CH3? We also know that each mole of methane you burn gives off 890 kilojoules. So I'm going to say 3.2 times 1 divided by 16 times negative 890. Ladies and gentlemen, you get negative 178 kilojoules for your 3.2 grams of methane. And that's really all that one's asking you to do. Okay. Here's a good old enthalpy of formation, and we're going to try to find the enthalpy of formation of octane. So I'm going to write the formation equation. Well, if you're trying to make octane, you're going to need 8 carbons, and you're going to need 18 hydrogens. That's 9 H2s. We're trying to find the heat of formation equation. It says using the enthalpies of formation and enthalpies of combustion. So the first thing that we're going to want to do is write a combustion equation for octane. Combustion equations always involve oxygen, and the products are always CO2 and H2O. I'm going to balance this, so this is going to be an 8, and this is going to be a 9, and this is going to be, what do we have here? 25 oxygens, and you can't have 25 oxygens, but you can have 25 halves. So we've got a balanced combustion equation, and I'm going to look on table B5 to find the energy of combustion of octane. It's right here, negative 5,470.5. So we're going to say this is our heat of combustion. Okay, let's write a formation equation for our carbon dioxide. We know from looking at our table here that the heat of formation of carbon dioxide is negative 393.5. Let's do the same thing with our water. You're making water with H2 and 1/2 of an O2. We want to specify liquid water because it's always a liquid in a combustion reaction. So, sorry about that. We're going to write a heat of formation of water. We're going to pay attention to the fact that we're using the liquid version, which is right here, negative 285.8. So we're going to say negative 285.8 kilojoules. All right, we've got all the information we need. What we're going to do is make everything in our target step equations look like our target equation. So I'm going to take this 8 carbons, I'm going to multiply everything in this equation by 8. And that means I'm going to take the energy and I'm going to multiply that by 8 as well. This becomes negative 3,148 kilojoules. Let's do the same thing with our hydrogen. Our hydrogen is currently being multiplied by 9 in our target equation. So I'm going to multiply everything in this step equation by 9. That means we're going to multiply everything that's in this bottom equation by 9. This is now negative 2,572 kilojoules. All right, we're almost there, except this is C8H18 as a product. Here it is as a reactant. What we're going to do is flip this entire equation around. Sorry, I had someone knocking on my door. So what we're going to do is we're going to take this entire equation and we're going to flip it backwards so that when we do this, now it's running in the opposite direction. That means 9 molecules of liquid water are going to react with 8 molecules of CO2. They're going to produce 25 halves of oxygen and 1 molecule of C8H18. When we do this, we're going to flip this sign to this energy change backwards. Okay, let's see if everything lines up like it should. 8 carbons as a reactant, 8 carbons. 9 H2s as a reactant, 9 H2s as a reactant. 1 molecule of C8H18 as a reactant. I'm sorry, as a product, and it looks like everything is lining up like it should. Everything else should cancel. So 9 molecules of liquid water gets produced and used up in this equation. 8 molecules of CO2 gets produced and used up in this one. And now we're trying to find out if 25 halves of an O2 on the product side is equal to the number of oxygens on the reactant side. It is if you rewrite oxygen instead of 8 molecules of oxygen, we say 16 halves. And that means that the 25 halves cancel out the 25 halves on the reactant side. Ladies and gentlemen, that means that these steps are the equivalent of our target equation. 5,470.5. We're going to add to that negative 3,148, and we're going to add to that negative 2,572. Ladies and gentlemen, your energy change for the formation of octane is negative 249.5 kilojoules. All right, let's do this one. Yeah, you're going to see this one's going to look pretty familiar because we've been using the wrong formula for our propane all day. Okay, so let's do it. We're going to write the heat of formation equation for propylene, C3H6. And we know you're going to need 3 carbons and 6 hydrogens, which we're going to write as 3 H2s. And we're trying to find the heat of formation. We're going to do that by writing a combustion equation for propylene. And we know you're going to react C3H6 with O2 to produce CO2 and liquid water. So I'm going to balance this by putting a 3 here, a 3 here, and that means that there are 6 plus 3 is 9 oxygens on the product side. We'll balance this by saying we have 9 halves, and we're going to look up on our table, which is right here, and the total heat of combustion for propylene is negative 2058, negative 2058 kilojoules. All right, so now what we're going to do is we're going to write a formation equation for our CO2, which we know from table B14 is negative 393.5 kilojoules. We're going to write a heat of formation for our water, which means you're going to react 1 H2 with 1/2 of an H2O to make 1 liquid water. And this is a heat of formation of negative 285.8. All right, all the pieces are in place. Now let's see if we can get them to look like our target equation. So 3 atoms of carbon here. I'm going to multiply everything in this equation by 3. That's going to make this negative 1180.5. I'm going to multiply everything in this equation by 3 to make it look like the 3 hydrogens in our target equation. And when I do that, I'm going to take negative 285.8 and multiply that by 3. This is now negative 857.4. The last thing I need to do is I need to take this combustion equation and flip it around backwards so that the C3H6 lines up on the right side. So we're going to say 3CO2 plus 3H2O yields 9/2 of an O2 and C3H6, and that means we're going to flip the sign of the energy change as well. All right, let's see if it lines up. 3 carbons lines up with 3 carbons, 3 H2s lines up with 3 H2s, C3H6 lines up with C3H6, everything else should cancel. 3 CO2s cancels out because it gets reduced in this equation, used up in this one. This one produces 3 molecules of H2O, which get used up in this one. And there are 9/2 of an oxygen molecule on the product side. Are there 9/2 on the reactant side? There are if I rewrite the oxygen as 6/2. 9/2 cancels 6 plus 3/2, and of course that works. So what we're going to do is add all of these up. We're going to say positive 2058. We're going to add to that negative 1180.5. We're going to add to that negative 857.4. And we get a barely exothermic number of positive 20.1. Okay, last one. Calculate the enthalpy of vaporization of water at 25 degrees Celsius using enthalpies of formation. Here's how we're going to do this one. What does it look like when we vaporize water? It means we add some heat to our liquid water, and that turns it into water vapor. So there's basically 2 formation equations for making water. One is going to be the formation equation for making liquid water, and according to our table, that has a heat of formation of negative 285.8. And we have a formation equation for making water vapor. That would look like this. H2 plus 1/2 of an O2 yields water vapor. And this has its own heat of formation, which is going to look like this. Negative 241.8. And so what I'm going to do is I'm going to treat this like our target equation, and I'm going to flip these 2 equations around to make it look like this. What that means is that I want my H2O as a liquid to appear as a reactant in this step equation, so I'm going to flip this one backwards. Now it's going to look like this. H2O as a liquid is going to break down into H2 and 1/2 of an O2. I want H2O as a gas to be a product, and it already is here, so it looks like all we have to do is treat this like this is our target equation, and H2O can be found as a reactant in one of our step equations. H2O as a gas is a product in our target equation, and here it is as a product in one of our step equations, and everything else should cancel. H2 cancels. 1/2 of an O2 cancels, and that means that because I flipped this reaction backwards, this is now positive 285.8. So all I'm going to do is add these together. I'm going to take positive 285.8 and I'm going to add to that negative 241.8, and we get our heat of vaporization. The amount of energy necessary to vaporize 1 mole of water is 44 kilojoules. In chapter 10, we saw that as 40.79 kilojoules, so they're pretty close. It doesn't really matter which answer we use, but mathematically, we get this one. So that's all it's really asking you to do. All right, good luck. Be ready for lab tomorrow. Goggles are not required. See you then.